Hello, welcome to this new video of Math-S400, Mathematics and Economic Modeling. In the lecture of today, we're going to see our final topic, which is a Nash equilibrium, the existence of a Nash equilibrium. So we're going to define what a game is, a normal form game, and we're going to define what a Nash equilibrium is. And then we're going to show the existence of a Nash equilibrium, and for this we're going to use Kakutani's fixed point theorem. Okay. So a Nash equilibrium is an equilibrium concept in economics, and it's used in game theory. So first, you have to define what a game is, in particular what a normal form game. Okay, so for a game, in order to play a game, you need a number of players. So let us denote this by the set n. So this 1, 2, 3, and so on. These are the players. So normally there's a finite number of players. So this is a finite set. And then each player can do something in the game, can take an action or a strategy. So normally there's a difference between actions and strategies in a game, but for normal form games, these two concepts are the same. So we're going to use the term AI to denote the action set of player I. Okay, so I is one of the players and AI is the action set of player I. So this set contains everything that player I can do. So in general, in this course, we're going to take AI to be a subset of Rk. And then K can differ from player to player, okay? But we're going to take it a subset of some k-dimensional Euclidean space. Okay, so actions are basically vectors. People can choose from a set of vectors. Okay, so what do we need? We have players. Players can do something. And then if every player has done something, we would like to see the payoff of the different players, right? So if every player does something, then every player picks an action AI from his set of possible actions, okay, and then we have a payoff. Okay, so what's the payoff? Well, in economics we normally use utility functions or payoff functions, which are the same in game theory. So this is a function u. So what does it do? It gives a real number r, and we allow the utility function to differ from player to player. So we will use a superscript I to denote the utility function of player I. And so what goes inside the utility function are the actions of the different players. Okay, so A1, something from A1, something from A2, until something from, assume that there are small n players in total, an. Okay, so I didn't leave enough room here, so let me denote it like this. Okay, so utility function basically gives you a number. For example, if player 1 plays strategy A1 and player 2 chooses strategy A2 and so on, then this is the payoff of player I if every player J picks action AJ. Okay, so this is the concept. And in general, what people would like to do is they would like to take an action that's optimal for them, given what the other players do. And this is going to define an equilibrium notion, and this is going to be called the Nash equilibrium. Okay, so an action profile, this is called a profile, right? An action for every player is called a profile. So A1, A2, until AN is a Nash equilibrium if for all players I and N, and for all actions AI and AI, the utility that player I gets when everybody else plays according to the Nash equilibrium, right? So I minus 1, this is the player before I, and then we have I plus 1 until an. Okay, so everybody plays according to the Nash equilibrium, and I forgot to put lines for all the a's because these are vectors. Okay, so you should think of these as potentially vectors. Okay, so here everybody plays according to the Nash except for player I plays strategy AI. Okay, and if player I would also play according to the Nash equilibrium, then everybody would play according to the Nash equilibrium. So you have the strategy A star I minus 1, AI star A star I plus 1 until A star n. Okay, and we have a Nash equilibrium if the second one is always greater or equal to the first one. So what does this mean for player I? If everyone chooses according to the equilibrium, then it will be optimal for player I to also pick the action that corresponds to the equilibrium. Okay, so player I has no incentive to deviate from the Nash equilibrium. So this is the important notion of a Nash equilibrium. Okay. So there's a famous result in economics, and this result gives a couple of conditions on the underlying structure, in particular on the set of actions and on the payoff functions here, such that Nash equilibrium always exists. And so what are the conditions that should be satisfied? Well, first of all, AI should be closed and bounded. Okay, so in other words, compact and convex. Okay, so these are normally standard assumptions that we need to have in order to apply Kakutani's 6-point theorem, right? So this is also where it comes from. So we assume that for every player I, B sets are compact and convex. And then concerning the utility function, we have that UI, so this depends on A1, AI minus 1, the action of player I itself, AI plus 1 until AN. So this is continuous and quasi-concave in own action. Okay, and the importance of the quasi-concavity will become apparent, but what does this mean is that if I fix the strategies of all the other players, again I forgot to put bars, so I fix these strategies, then if I see this as a function of this variable alone, then it's quasi-concave in this vector here. Okay, so that's what it means to be quasi-concave in own action. So there's a famous theorem of Nash, right? So this is also why it's called the Nash equilibrium, who says that if this condition is satisfied and this condition is satisfied, well then we know that there's going to be, for all I and N, for all players, there exists an action AI such that the action profile is a Nash equilibrium. Okay, so in particular it satisfies this condition here. Okay. So what's the idea behind this result? Well, the idea behind this result is to first write the Nash equilibrium as a kind of fixed point of a correspondence. Okay, then the existence of a Nash equilibrium boils down to the existence of a fixed point of this correspondence. And then we use Kakutani's fixed point theorem in order to show that actually such a fixed point exists. Okay, but of course, in order to verify Kakutani's fixed point theorem, we need to be sure that all the conditions for this theorem to hold are also satisfied in this setting. So as you may have noticed, if we have a lot of players, this notation becomes very elaborate. So what I'm going to do from now on is that I'm going to restrict myself to 2 players. So I'm going to only look at 2-player games. This will make the notation much easier, but the theorem and the result and the proof can easily be generalized to more than 2 players alone. Okay, but just for convenience, assume that n, the set of players, is 2. Okay, so then the action sets are A1 for player 1 and A2 for player 2. Okay, and then we have a utility function U1 that takes as argument A1 and A2, and we have U2 that takes as argument also A1 and A2. Okay, so here we have that these are convex and compact, and these are continuous, and that U1 is quasi concave in A1 subindex, and U2 is quasi concave in A2. Okay, so these are the conditions that we will use. So we're going to use this setting of a 2-player game. So let's look at the problem of player 1. Okay, so the idea behind the Nash equilibrium is that every player takes the action of the other player as fixed, right? Under the idea I cannot influence this, right? Because every player decides on their own what to do. But given what the other player does, I'm going to choose the best possible action that I can take. Okay, so the goal of player 1, okay, is to maximize her utility. So this is U1, A1, A2. So here A2 is a fixed parameter, right? This is what the other player does, but A1 is the variable that you maximize over. Okay, so subject to what kind of actions can player 1 pick? Well, player 1 can pick any action in her action set, so A1 has to be in the set A1 of actions. Okay, so this is a standard maximization problem, as you have already seen several before. Okay, so if you solve this maximization problem, what you will get is a value. Okay, and this value will depend on the parameter of this problem, which is here A2. Okay, so this is, if you go back to Burgers' maximization theorem, this is similar to the theta, the parameter that we had before. Okay, so this will give you a value function for player 1, which only depends on A2. Okay, and of course, if we solve this problem, we can put all the solutions to this problem in the solution correspondence, and we're going to call this B1. Okay, so B1 is similar here to what we called in Burgers' maximization theorem, gamma of theta. But now theta is A2, right? So B1 will depend on A2. So what's this? These are all the actions A1 and A1, such that U1, A1, A2 is equal to V1, A2, the best possible payoff that this player can get. Okay, so this is also called the best response correspondence. So the idea behind the name is very simple. It's the best thing that player 1 can do given what player 2 does, right? So it's the best response of player 1 to the action A2 of player 2. So what are the properties of these functions? Well, from Burgess maximization theorem, we know that this is continuous by assumption, and this is a compact set and convex. Okay, so first of all, we know that this is continuous. Okay. More importantly, what do we know about the solution correspondence? Well, we know that solution correspondence is upper hemi-continuous. Okay, that's the first thing. Second, because A1 is convex, so normally here for Burgess maximization problem, we had that this was a correspondence depending on theta, right? So in general, here you should have a correspondence that depends on A2, but here for every A2, the set A1 is the same. Okay, so basically we have a correspondence that's fixed, that doesn't vary over A2. Okay, so anyway, if you have correspondence like this and this set is convex, then we know that this correspondence of the constant correspondence of A2 will be convex valued. This is like a convex valued correspondence of A2. Well, simply because it doesn't depend on A2, and it's a convex set by assumption. Okay, so we have seen that if this correspondence here is convex valued, and if this is quasi-concave in the own strategy and the thing you're optimizing with, then here this B1, the solution correspondence here, will be also convex valued. Okay, so this is derived in the part on convexity that we also have seen before, right? So you see in this lecture all the previous results are integrated into one, and we will use these two properties actually to show that there exists a Nash equilibrium. Okay, so this is for player 1. I can do a similar thing for player 2. Player 2 will try to maximize A2, his utility function that depends on A1 and A2, subject to A2 being in the strategy set A2. Okay, if you solve this, you get an optimal value function which depends on A1, and you will get the best response correspondence A1, which depends on A1, which are all the actions A2 in A2 such that utility 2 of A1 A2 is the best optimal thing that player 2 can obtain, which is V2 A1. Okay, so this is the best response correspondence of player 2. And similar as before, given all the conditions that we imposed on the problem, we know that this is upper hemi-continuous, and we know that this is convex valued. Okay, and these are two properties that we're going to use. Okay, so let's go to back to the definition of a Nash equilibrium. A1 star, A2 star, let me fix the focus, is a Nash equilibrium. So remember what this requires. Well, it requires that for all A1, U1 of A1 star, A2 star is greater or equal to U1 of A1, A2 star. So if player 2 plays at the Nash equilibrium, then the best that player 1 can do is also play at the Nash equilibrium. Okay, and we have a similar thing for player 2 for all A2 and A2. Okay, U2 of A1 star, A2 star is greater or equal to U2 of A1 star, A2. If player 1 plays A1 star, then the best thing that player 2 can do is also to play A2 star at the Nash equilibrium. Okay, so here, if you're at the Nash equilibrium, no player has an incentive to deviate, to do something else that would give him or her higher utility. So this is basically saying that if we translate this to a maximization problem, this is basically saying that A1 star is in B1. Did I use superscripts or subscripts? Let me double check. I used superscripts. Okay, so this is good. Of A2 star. So it's the best response correspondence of player 1 to A2 star. Okay, so then this here maximizes the utility when player 2 plays A2 star. Okay, so it's in the best response correspondence. This condition here says that, actually it's not a condition, but it's an equivalence, right? That A2 star must be in the best response correspondence of player 2 given A1 star. So A1 star is in the best response correspondence of player 1. A2 star should be in best response correspondence of player 2 given that the other person plays in Nash equilibrium. So this already has some kind of a flavor of a fixed point, except that here we have A1 star and here A2 star, here we have A2 star and here A1 star, right? So in some sense we would like to group these two things together and define kind of new correspondence that makes this into a fixed point kind of argument. Okay, and you can easily do this. So what do? We define something like a joint best response correspondence. Okay, so here, remember B1 was a correspondence, so what goes inside the correspondence is an element of A2, and you get a subset of A1. Okay, B2 takes an element of A1 and gives you a set of actions for player 2, so something in A2. And if you want to have a fixed point, then what we start with has to be mapped to itself, right? You need to go from a set S that we have seen before to the same set S, right? So we would like to join these two sets here, and you can do this by taking the Cartesian product. Okay, so we're going to define a correspondence that takes an action of player 1 and an action of player 2 and gives a subset of player 1, player 2 actions. Okay, and we're going to define it according to this rule. So if I plug in an action of player 1 and player 2, what am I going to get? Well, I'm going to get a new action, a subset of actions of player 1 and actions of player 2, right? So it's going to be a set. So I can call this action B1 and B2 in A1 times A2, and I'm going to say that B1 is the best response of player 1 to A2 and B2 is the best response of player 2 to A1. So B1 is in B1 A2, so these are all vectors, and B2 is the best response of player 2 to an action in action A1 of player 1. Okay, so this is how I'm going to define this joint best response correspondence. Okay, and my claim is now that a Nash equilibrium, every Nash equilibrium is a fixed point of this correspondence. Okay, so how can you easily see this? Well, take a fixed point of this correspondence. So let me say that A1 star A2 star is a fixed point, so it should be in B of A1 star A2 star. So if I look at the definition here, then B1, so A1 star should be best response of player 1 to the action of player 2, which is here A2 star, and B2, which is here A2 star, should be a best response of player 2 to here A1, which is this one here, and you see that this is A1 star. Okay, like this. So you see that indeed this coincides with the definition of a Nash equilibrium. Okay, so every Nash equilibrium is a fixed point of this correspondence, and every fixed point of this correspondence will be a Nash equilibrium. So in order to show that there is a Nash equilibrium, the only thing that we need to do is that this correspondence B here has a fixed point. And for this, we're going to use Kakutani's fixed point theorem. Okay, so we call B A1, A2. These were all the actions B1, B2, and A1 times A2, such that B1 was the best response of player 1 to A2, and B2 was the best response of player 2 to A1. And we would like to show that this has a fixed point, so we're going to verify the conditions of Kakutani's fixed point theorem for this correspondence. Okay, so let's go over them one by one. So first of all, we need to have conditions on the domain. Okay, so we have A1 times A2. So what do we know? We know that this set here is compact and convex, and we know that this here is compact and convex. Okay, so what's A1 times A2? So you can imagine this being a stacked vector, first of an action A1 and then of an action A2 on top of each other, right? So this Cartesian product, you can imagine it as being just taking a vector of A1 and then below taking a vector of A2. Okay, and you see that if this is bounded, if all the set A1 is bounded, so these are bounded and these are bounded, then the set of all these vectors also will be bounded. Okay. Likewise, if I have a sequence of these larger vectors that converges to a vector, then for the first component, the limiting vector will be an A1. For the second component, the limiting vector will be an A2. Okay. So the limiting vector will also be an A1 times A2. Okay, so this set here will also be compact. And you can do the same for convexity, right? If I have two elements in A1 times A2, right, and the convex combination of the two first components will be an A1, the convex combination of the first two components will be an A2. So if I take the first convex combination of the first components and then the second components on top of each other, it will be an A1 times A2. So here A1 times A2, which is the domain of this correspondence, will satisfy the condition that it's compact and also that it is convex. So these conditions are necessary conditions for Kakutani's fixed point theorem to apply. Okay, so we have seen that the domain of the correspondence B is compact and convex valued. Now we still have to show that the correspondence B itself satisfies the properties of Kakutani's fixed point theorem. In particular, it's non-empty, it's convex valued, and it's upper hemicontinuous. So maybe we can rewrite a little bit differently. So as I said before, basically what we can do is we can take a Cartesian product, we can stack the vectors on top of each other. So if B1 and B2 then is in the best response of A1, A2, okay. Well, by definition, this is the same as saying that B1 is the best response of player 1 to A2, and B2 is the best response of player 2 to A1. Okay, so these are the same definitions, just stated in another way. So let's first show that B is upper hemicontinuous. Okay, so let's check the definition of upper hemicontinuity. So what do we need? We need a sequence of elements in the domain. Okay, so I will use the first subscript to denote the player and then the second subscript to denote the element in the sequence. Okay, so we have a sequence A1n and A2n. Okay, let's tag them in the vector. And this should converge to something, let's call it A1 and A2. And then we have also a sequence of B1s, B2s. Okay, and for all n and n, B1n, B2n is an element of B, A1n, A2n. Okay, so we have to show two things. First of all, we have to show that this sequence here of B's is bounded. And then second, we have to show that if this sequence converges to something, then the limit should be in B of the limit of the A's here. Okay. So property 1, we have to show that this sequence B1 and B2n is bounded. Well, it's not so difficult, it's just a bit of notation. So what we're going to do, we're going to split it back up with respect to the correspondence of player 1 and the correspondence of player 2, because we know that these here are both upper hemicontinuous, right? And then we're going to use the property of upper hemicontinuity of both of them in order to show upper hemicontinuity of the joint one. So if we use this, then we can split this up into A1n converging to A1 and A2n converging to A2. Okay, so let me put this in red because this, I'm going to take the red and the greens together. Okay, and here, this here, we can use this definition here. Okay, so I have that B1n is in the best response of player 1 with respect to A2n, which is this red here, and I have that B2n is in the best response of player 2 given A1n. Okay, so this is just a restatement of this into the separate best responses. Okay, so if you look at the two green ones, we have that A1n converges to A1 and B2n is in B2 of A1n. And I have that B2 is upper hemicontinuous. So it follows immediately that B2n is bounded. Okay, so this is by upper hemicontinuity of B2. Also, if you look at the two reds, A2n goes to A2, B1n is in B1 of A2n. I have that B1 is upper hemicontinuous. So from this it follows that B1n is bounded. Okay, and if B1n is bounded and B2n is bounded, well then if I stack the two vectors, let me use black, then B1n, B2n will also be bounded. Okay, so if you have stacked vector and every element wise they're all bounded, then this entire vector is also bounded. Okay, so this proves the first part here. And now for the second part, in order to make it more clean, let me rewrite actually what the derivation is. What we need to show is the following, that if A1n, A2n converge to A1, A2, and for all n, B1n, B2n are in the best response given A1n, A2n, and if b1n, b2n converge to some vector, let's say b1, b2, well, for any such system, I need to show that b1, b2 is in B of a1, a2. Okay, so this is what I need to show. And again, I'm going to use the fact that I can split these two things into the best responses of player 1 and player 2. Okay, so again, I'm going to use the green one, that a1n converges to a1, and red that a2n converges to a2. Then in red, I'm going to use that b1n is in the best response of b1 given a2n. In green, that b2n is in the best response of player 2 given a1n. Right, so here I'm just restating this part and this part by these conditions, right? These are equivalent. And then for the last one, I can again split this up into two parts, right? So b1n converges to b1, and b2n converges to b2. Okay, so if I take all the green bits together, I have that a1n converges to a1, b2n is in the best response player 2 of a1n, and b2n converges to b2. So by upper hemicontinuity of b2, I have that the limiting vector here, b2, is in b2 of the limiting vector of the a's, which is a1, this one here. Okay, and if I take all the red parts together, I can use a similar upper hemicontinuity of b1 to show that b1 is in b1 of the limiting vector a2. Okay, and if I take these two together, and then by definition I have that b1, b2 is in the best response of a1, a2. Okay, so this proof is quite simple. You just have to split everything up. It's a little bit heavy in terms of notation, so you have to keep track of where is player 1, where is player 2, which kind of these arguments do I need to take together and which not. Okay, but and then anyway, this shows that this correspondence B here satisfies the first property of upper hemicontinuity and satisfies the second property of upper hemicontinuity. So all we are left to show now is that the last property is satisfied. In particular, B is convex valued. Okay, and for this we use what we have shown before, is namely that B1 and B2 are separately convex valued. Okay, so what do we do? Well, take two vectors in B for a given set of strategies, let's say A1, A2. Okay, so for example, we have B1, B2 is in there, and maybe C1, C2, which is another pair of strategies, is also in the best response with respect to A1, A2. Then you have to show that every convex combination of these two is also in B of A1, A2. So we're going to again use the definition. We're going to split it up into best response of player 1 and best response of player 2. Okay, so here for the first, let me use green and red again. So we have that B1 by definition is the best response of player 2 with respect given A1. You have that B2 is the best response of player 1 given the strategy A2 of player 2. Here we have that C1 is the best response of player. Yeah, I made the same mistake. So the green, I switched to 2 players, right? So let's take the first one here and let's try not to make a mistake. B1 is in the best response of player 1, right? It's an action of player 1 for A2. And we have that B2 is the best response of player 2 for the action A1. Okay, so far so good. And then here we have that C1 is in the best response of player 1, also for action A2. And here C2 is in the best response of player 2 for the action A1. Okay, and now we're going to take the green and the red together, and we're going to use convex valuedness of B1 and convex valuedness of B2. So in particular, if we use the fact that B1 is convex valued, then we have that the convex combination of B1 and C1 should be in B1 B2. Okay, and here if we take the convex valuedness of B2, then we have that convex combination of B2 and C2 is in B2 A1. Okay, so here you have that alpha is between 0 and 1. So this follows here from the fact that both B1 and B2 are convex valued. So now we can use the definition of B again, and from this it then follows that alpha B1 plus 1 minus alpha C1, sorry, I forgot to draw some lines, and the second part is alpha B2 plus 1 minus alpha C2 is in the best response given A1 and A2. So again, we have 2 vectors and the correspondence for a given A1, A2, and the convex combination should be in B of A1, A2. So here we took any arbitrary alpha, we use convex valuedness of the best responses separately. So we see that indeed the convex combination here, indeed this is equal to alpha B1, B2 plus 1 minus alpha C1, C2. So this convex combination of the 2 separate strategies is in B of A1, A2. Okay, so we have shown that this correspondence B here is upper hemicontinuous. We have shown that it's convex valued. So Bakker-Kutani's fixed point theorem, it has a fixed point, and then this fixed point will be a Nash equilibrium, as we have seen before. So this concludes the proof of the existence of a Nash equilibrium. And this also concludes these lecture series. So thank you for watching.